So I'm going to go ahead now and solve a group of problems from Chapter 5. This is the chapter on circular motion, centripetal force, and universal gravitation, also Kepler's laws. It's a very interesting topic, and so let's get into it. So you can sort of see here, oh, that's not the first one I want to do. I think I want to start here. There we go. So we'll start out, again, this is Chapter 5 in the textbook. Start out with numbers 2 and 3 because they're both pretty short problems and we should be able to do them pretty quickly. And I know number 1 is assigned as homework, so hopefully this will help you get started with those if you need any help. So number 2, it tells you a jet plane is moving with this velocity, and it excuse me, and it pulls out of a dive by moving in an arc with this radius. So we're executing uniform circular motion, right? So we know immediately there's going to be a centripetal force, and they want to know what is the plane's acceleration in g's, right? So pretty much this plane's moving in a piece of circular arc, so we have a centripetal force, right? Centripetal force, Fc. Sometimes the book calls this Fr for F radial. It means the same thing, right? Sort of do that like there, or F radial. They mean, again, the same thing. They're used interchangeably. And the formula for this is mv squared over r. And this is the centripetal force. Now, we do not have the weight of this jet plane. Let's see here, moving in an arc. Actually, I actually oversimplified this, so you got to see me make a mistake here. Let's see. Let me just go through this really quickly. Okay, I think this is the right idea. I think this is actually what's happening. So we have this plane, right? And initially it's diving like this. This is number 2. Right? I was oversimplifying it. So we have initial plane, it's diving like this, right? So it feels, initially this is the force that it feels, right? And then suddenly it's going to exert an upward force, right? And so let's see. Oh, actually, it is easier than that. Sorry, 2 mistakes in one day. Not so hot for me. I was right. So the net force is the centripetal force, right? But basically what we want to look for here is the centripetal acceleration. We don't need the force. This is also interchangeably called the radial acceleration. And this is just equal to v squared over r here. And so we could basically just plug this in. So this is going to be 525 meters per second. And our radius here is 5.2 kilometers. We obviously have to put that into meters. So that's 5.2 times 10 to the 3 meters. And this is this quantity squared. So let's go ahead and do that. So 525 squared divided by 5.2 times 10 to the 3. And when I go ahead and do that on my calculator, I get 53 meters per second squared. And when they want to know how many g's this is, right, basically you're just going to divide this by 9.8. So basically you're going to say, okay, this is to do, let's say, the number of g's, right? Basically we're like, how many multiples of gravity is this? So it's going to be 53 meters per second squared over 9.8 meters per second squared. So let's divide this number by 9.8, and we get about 5.4 approximately. So it's going to be 5.4 g's. Or just, you would actually don't have to do the possessive, just leave it as 5.4 g. So this acceleration is 5.4, the multiple of the gravitational acceleration on the Earth's surface. Number 3 rather. Horizontal force of 310 newtons is exerted on a ball as it rotates at arm's length in a horizontal circle, and they want the radius, and they give you the radius. So basically the picture is like this, right? And do they say it's on like a table or something? Okay, so it's a 2 kilogram ball, and it's a horizontal force. Okay, so basically the idea is this, right? You almost want to think of it like this, right? So we have like a 3-dimensional space here. Call that y, call that x, and you could even call this into the page, you can call it z. And so this thing is spinning in the xz plane, right? So it's never moving in the y direction. So here's our ball, like right there, m, and it's in the xz plane, right? So it's sort of moving. The circle is moving sort of like this, right? But it's never going in the y direction. It's just in the xz direction. It's because like y is sort of like up like that. This is just one way to think of it. So, okay, now they tell you that there's a horizontal force of 310 newtons, and it's at arm's length, right? So this is our radius here, right? That's the radius. And if this thing is going to, let's just say for the sake of argument, that this thing is moving counterclockwise, so like this is the direction of it, right? So it has a linear velocity at any point like that, right? It wants to move off at a tangent to the circle at any point, but it doesn't, which means it's held in orbit by a force that points to the center, right, by Newton's first law. So, and we know that the force, right, it's probably going to be a tension, but let's just call it a force, right? There's a force acting on the ball in this direction, right? So if we were to do the free body diagram for this ball, it's like this, right? So here's the ball, and there's a horizontal force acting like this, right? That's the horizontal force. And the net force is also to the left, right? So then we call this F net is like this, right? F net. And F net is equal to the centripetal force, right? Or the radial force. The centripetal force is not a new force, right? It just denotes the direction of the net force. So when you set this up, right, if we do Newton's second law, we're going to say the sum of the forces, let's say, in the x direction is equal to the centripetal force. What force is acting in the x direction? Well, they give us a number for that. They say it's 310 newtons, right? So it's 310 newtons equals mv squared over r. And I believe they're looking for v here. That's right, the speed. Now we're ignoring gravity, right? Because I'm assuming maybe this is on like a frictionless table. If you have gravity here, this gets more complex because you're going to have a force sort of pulling it down like that, mg, and this thing is going to become sort of tilted. It's going to become like a cone almost, and that's not super hard, but it gets a little more complex. Anyway, we can go ahead and solve for this quantity here. So if I do the algebra, what we're going to get is this is going to be the square root of r times 310 newtons divided by the mass. And so the velocity here, and we know the r is 0.9 meters. So this is 0.9 meters times this 310 newtons divided by the mass is 2 kilograms. And so let's see what we get there. So square root of 0.9 times 310 divided by 2. And that gives us about 11.8 meters per second. Okay. So that's the answer to that one, assuming we ignore gravity. Here, a little more complex. So there's a guy, make this picture a little bigger. All right. So there's this guy swinging, and he's swinging in a piece of circular arc, and they tell you that he can exert a force of 1150 newtons, and they want to know at the lowest point of his swing. They give you his mass, and they give you the vine length, and they want to know what's the max speed. So the idea is this, right? So we have, like, here's the vine or whatever. Yeah, that's our vine. And here's the mass. This is the guy, Tarzan. And he's swinging like this, right? So and we'll call this the radius r. That's the terrible r. Do that a little more coherently. It's also a really bad r. There we go. And he's doing this sort of piece of arc, right? So at the bottom, he's here. So it's a piece of circular arc that he's executing. So at the bottom, he's like right there. So what forces are acting on him? Well, there's the weight, his weight, right? And there's also the force that he's applying, call that F, and that has to be longer. I'll explain why. There's a tug of war going on. The reason the blue vector needs to be longer than the red vector is because his net force is up, right? It's radially to the center, right? FR. So there's this overall radial force pointing up. How do we know that? Well, he is about to start, he's finished his descent, and he's about to begin his ascent. So he's going to be moving upward along the circular arc. So the net force, the radial force, has to be up. So if we go ahead and apply Newton's second law, right, it's going to be the sum of the forces, I guess we'll just call this the y direction since we're looking at things vertically, is equal to the radial force, right, or the centripetal force. So, or you can call it Fc if you want. Same thing. But we'll just leave it as radial force for the moment. What points up? The force that he applies, right, minus the weight, right, because that's the tug of war, and that equals mv squared over r. And again, we're looking for v, so I'm going to go ahead and do the algebra really quickly here. I would definitely encourage you to go ahead and double check this on your own. This is going to be rf minus, just work it out, I'm sort of doing this in my head, it shouldn't be too hard, rf minus GR, or RG, right, all divided by, well, let me, sorry, do that again. V is the square root. We'll keep the R out there. It's a little neater. So this will be F minus mg, right, all over m. This is probably the fastest way of going ahead and doing this. So let's see what we got. R, right, the radius you're told is 4.7 meters. The F is 1150, right, 1150 newtons. Minus his mass is 78 kilograms, right? So 78 kilograms times 9.8 meters per second squared. Close that up. Divided again by, that's a parentheses there as well, divided again by 78 kilograms. So I'm going to plug this into my calculator and see what I get, so just bear with me for a second. So 1150 minus 78 times 9.8, that's that, times 4.7, divided by 78 again, square root of that number, and I get 4.82 meters per second. So that's the max velocity given the force that he's capable of exerting, that he can tolerate. Okay. Now we're going to move on to gravitation. This is Newton's law of universal gravitation. Very interesting topic. Obviously relates to circular motion because the orbital trajectories are, well, they're ellipses, but in many cases they approximate circles, particularly in the inner solar system. So before we even get started, right, Newton's law of universal gravitation says that the gravitational force between any two objects is G, m1, m2, over r squared. This big G is the universal gravitational constant, and the number for it is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. This is a very weak, a very small number. They sometimes call this the gravitational coupling constant, but it's small. It's 10 to the negative 11. So that gives you a sense of how weak gravity is. In fact, it's the weakest of the four fundamental forces. The only reason we even notice it is because the mass of the Earth is so enormous. But it's completely, say at the atomic level, it's completely washed out by the electromagnetic force and then the nuclear forces. Anyway, it works very well despite that. So they say two objects attract each other gravitationally with a force of this when they are this many meters apart. Their total masses that find their individual masses. So we don't know what m1 and m2 are individually, but what we can say is that m1 plus m2 equals 4, right, 4 kilograms. So I can solve for one of these. I can say m1, right, I'm just going to leave the units out for a second just to make life a little easier, is that. And then I'm going to go ahead and take this thing and plug it in here. So this is a substitution problem. So I'm going to take m1 and plug it in there. And so when I do that, right, we're going to get this, that F, F, the gravitational force, I'm just going to leave it as F for the time being, is G 4 minus m2 times m2 over r squared. Now, you have to distribute, there's a couple ways of doing this. What I would probably do is distribute this m2 to these terms here, and you'll hopefully eventually start to see where we're going here. So it's going to be F equals G, and what we're going to end up with here is 4m2 minus m2 squared over r squared. And now I'm going to cross, this is like f over 1, so I'm going to cross multiply. So I'm going to get, here it's going to be G 4m2 minus m squared, or m2 squared, equals fr squared if I cross multiply. And now I'm going to divide both sides by capital G. So it's a lot of algebra here, more algebra than physics when you get down to it. Is equal to this. And now I'm going to bring everything over to one side. I'm going to bring everything over to the right-hand side. So we're going to get m2 squared minus 4m2 plus fr squared over g equal to 0. And this is a quadratic equation because the unknown is m2, right? So you can almost, if you want, think of this as like x here, right? This looks like almost like this, right? It's like, well, we get a number for this, right? So let's get a number here first. So this thing, because we have numbers for these. right? F, we're told that F is 2.5 times 10 to the negative 10, and R is 0.25. Is that right? 2.5, yeah, times 10 to the negative 10. So let's get this, right? So this is going to be 2.5 times 10 to the negative 10 newtons. That's the force. R is is it 0.25? Sorry for that. 0.25, yes, squared. Divided by 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So we're going to put a number in here. Get that as a number, and you'll sort of hopefully see where I'm going with this. So just bear with me. Times 10 to the negative 10 times 0.25 squared divided by 6.67 times 10 to the negative 11, and I get 0.23. Right, so this whole thing is 0.23. So what was the point of that? The point is you can sort of rewrite this. Let's call it x instead. It'll look more familiar. Call that x squared minus 4x plus 0.23 equals 0. And this is a quadratic equation, right? And you can solve this using the quadratic formula. So this will be negative, right, just as a reminder, negative b plus or minus b squared minus 4ac, the whole thing over 2a. So b is negative 4, so this will be negative 4 plus or minus the square root of negative 4 squared minus 4 times 1, and c is 0.23, all divided by 2 times 1. So when we plug these numbers in, we're going to get the following. So this is 4, so x equals 4 plus or minus, and then in here we have 16 minus, let's see, 4 times 0.23, that's 0.92, all divided by 2. Right? So that'll be, no, so I'll do this part here first. I'll take 16 minus 0.92, right, and then take the square root of that. It's going to be pretty close to 4, 3.88. So it's 4 plus or minus 3.88 divided by 2. And then we have two options here. We can take the plus option or the minus option. So we'll call this M2 at this point, right? This could be either 4 plus 3.88 over 2, right? Or 4 minus 0.388, sorry, 3.88 over 2. Right, and these numbers will be, let's do the first one first, so that's going to be 7.88 over 2, right? So 7.88 divided by 2, 3.94 kilograms. Like that. And then this one is going to be 4 minus 3.88 divided by 2. It's a much smaller number, obviously 0.06, right? So that's what M2 potentially is equal to. In these cases, right, but either of these is plausible, right? I mean, there's nothing inherently wrong with either of these. Sometimes you'll get a negative number, in which case you know that's wrong because you can't have a negative mass. But these are both potentially, these are theoretically fine, right? So basically these are the options because they have to add to 4, right? So if M2 is 3.94, then M1 must be 0.06. And if M1 is 0.06, or sorry, if M1 is 3.94, then M2 must be 0.06. So you'll never know which is which, right? But you can say that these are the two masses for sure. So, because they sum to 4. So, there you go. Let's take a look at this one, number 32. So here, they tell you a hypothetical planet has a radius 2 times that of the Earth, but the same mass. What is the acceleration? So here we're looking for g, right? This is the acceleration. And the formula for g, right, is this, right? We treat it on near the Earth's surface. If we use the radius of the Earth and the mass of the Earth, this ends up being 9.8, 9.81. But here, so there's a couple ways of doing this. We can do this using actual numbers, or we can do this using proportional reasoning. I'll do it both ways. First, I'll do it proportional reasoning, right? We know on Earth that g, we'll call this g of Earth, right, at the surface, that's about 9.8 meters per second squared. Now, you can say that g is proportional to 1 over r squared. So if you double r, So basically, right, it's going to be like this number becomes a 2. So it's going to be like 1 over 2 squared, which is 1 over 4. So the planet, so this new g on planet X, right, should just be 1/4 g on the Earth, which is going to be 9.8 over 4, 9.8 meters per second squared, divided by 4, which I think is 2.45, yeah, 2.45 meters per second squared. Okay. So that's just proportional reasoning. You double, because it's an inverse square law, right? You double it, it diminishes it by a factor of 4. So you could actually do this thing, call this method 2. You could do this more formally. You could say, okay, the mass of the Earth, right, which is the same thing as the mass of this planet X, whatever you want to call it, that's 5.98. This is something you would look up in the book, is this. And the radius of planet X is twice the radius of the Earth, right, which is going to be 2. And again, the radius of the Earth, the average radius, something you would look up, is 6.37 times 10 to the 6 meters. So when you go ahead and get that as an actual number, you're going to get 1.27 times 10 to the 7 meters. And now you can go ahead and actually just calculate g that way. So g on planet X, right, that's big G, the mass of planet X over the radius of planet X squared. So this will be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times the mass, which is 5.98 times 10 to the 24 kilograms, all divided by this radius, 1.27 times 10 to the 7 meters squared. And if you run through those numbers, you'll get about, again, 2.45 meters per second squared. So the same as you got using just straight proportional reasoning. Okay, last question. This is going to be Kepler's third law here. So it tells you that Neptune is an average distance of this from the Sun, and they want to estimate the Neptunian year using the fact that the Earth is this far from the Sun on average. So here, Kepler's third law says this, that basically the square of the period is equal to some constant that doesn't ultimately matter in this problem times the cube of the radius. This is Kepler's third law. It's a way of just relating the orbital radii to the orbital periods. So basically, right, you can solve for k here, and you can say, okay, well, k is therefore going to be this number here, like that. And so you can basically just, k is always going to be the same, so this ratio is going to be the same, basically, right? So what we can end up doing here, let's see, so Neptune is an average distance, right, okay, so basically we could just be like, all right, T1 squared over R1 cubed is equal to T2 squared over R2 cubed, right? This is similar if you've ever taken chemistry to like when you do sort of like Boyle's law or Charles's law, the ideal gas law, and you're like P1 V1 equals P2 V2, that kind of thing. We'll say that 1 is the Earth, right, and 2 represents Neptune. It doesn't matter, just pick one. So we're looking for T2. We're looking for the orbital period of Neptune, right? So T, if you go solve for T2, do the algebra, cross multiply, and do everything you need to do. What you're going to end up with is this. So you're going to get R2 over R1 cubed, the square root of that times T1, okay? And we'll say that T1 is 1 Earth year, right? T1 is 1 Earth year, right? Because that's the amount of time it takes to go around the Sun once. So the Neptunian year, right? Neptune being 2, right? So so R is 4.5 times 10 to the 9, and for the Earth it's 1.5 times 10 to the 8. So 4.5 times 10 to the 9 over 1.5 times 10 to the 8. These are both meters, right? Cube that, and then take its square root times 1 year. So let's see what I get. So 4.5 times 10 to the 9 divided by 1.5 times 10 to the 8. I get 30. And then I'm going to go ahead and cube that number. Right, then take the square root of that number. That's 164.3. So one Neptunian year is approximately 164.3 Earth years. So it takes a long time for Neptune to get around the Sun. So anyway, I hope you found these problems useful, and there will be more coming soon.